So as always, please take a good look at the solutions and the rubric before requesting a regrade. And if you do request a regrade, it should be because you think the rubric was evaluated incorrectly. Yeah, and you have until the final exam to submit regrade requests. Okay, what do we think? I don't think that was the hardest quiz I've ever written. So yeah, the next quiz will be in 2 weeks. I don't know exactly what the material that's going to be on it will be, because usually I have quiz 4 the week after quiz 3, and it's usually on like 2D collision problems. I still might have it on those. Like that's what all the practice quizzes are on and stuff. And we usually leave angular momentum and torque for the final, which I'm still inclined to do, but we'll see. I'll update you on that very soon. But I might not have practice quizzes and stuff today, but at the latest tomorrow. And again, 2 weeks is when your next quiz is. Also, just like a side announcement, I'm sure all of you are aware, and probably most of you were affected significantly by the strike that we had last quarter, which was cool that we're going to get paid more, not soon enough and not enough, but we will, and that's great. But there's I just got like forwarded a letter from like one of the faculty and like instructors union, something like that. But the school is trying to push that extra money that they have to pay us onto our departments and our advisors, which ultimately just means they want to employ less grad students and make your classes bigger, which isn't great. So right now the letters and like petitions I've seen are mostly faculty saying like, hey, don't do this, but I'm sure that something will come around for like students to sign soon enough, because it's absolutely something that affects you. So if I get one of those, I'll forward it to you. And I think, yeah, it'd be in your best interest to let the school know that you don't want your sections to be bigger. And maybe like we'll break some more of the chairs in the DL room just to really emphasize that our sections are too big. Okay. So yeah, today I'm just going to do some more like in-depth review of concepts that we've already been over, and then I'll add a little bit of new material at the end. But even that is more of an extension of stuff we already know. So we left off with force and momentum. So forces, we know they're pushes and pulls, and they're vector quantities. The units are newtons, so they have a magnitude and a direction. And net forces, so when you sum all the forces up that are acting on an object, if that net force is not 0, then the object's motion, or its momentum, will change. Right? So you don't need a force to keep a constant momentum, but if there's any change in momentum, that could be speeding up, that could be slowing down, or it could be turning even with the same speed, that is some delta p. It's a change in your momentum vector, and it comes from a net force. Right. So what is momentum? Well, it's defined by mass times velocity. So the momentum vector points in the same direction as our velocity, and it's just kind of scaled by the mass of the object. Heavier objects and faster moving objects have higher momenta. And like I said, we need a net force on an object to change its momentum, to give us some delta p. And this equation down below gives us exactly how that happens. We need not just a net force, but a net force applied over some amount of time, delta t. Right? The longer amount of time you apply the force, the more impulse you get. So we often describe delta p or delta t as j net, the impulse vector. It's really just kind of an extra variable, if you ask me. Like if it helps you to think about like f net delta t gives you how much impulse that force delivered, and then that impulse is also equal to the change in momentum, fine, but I almost always just write delta p equals f net delta t because it's easier. But yeah, impulse is just a vocab word that we want to know. And applying this net force changes the object's momentum. Right? These three equations, an important thing to note is that this tells us that delta p, f net, and j net all point in the same direction. When you have an equation where one vector is equal to another vector, maybe multiplied by a scalar, like delta t, we know that just stretches the vector. But when you have vector equals vector times whatever, that means they're in the same direction, which makes sense, right? If I apply a force to the east, then my change in momentum as a result of that force should be to the east. And the net impulse that was delivered by that force is to the east. So that's just an important little subtlety there. When we have multiple objects that we define in our system, we can define the total momentum of the system just by adding all the momenta together. Right? We call it a closed system if there's no net force, which means that the sum of the changes in each of the object's momentum has to be 0. In other words, the only change in momentum that occurs are exchanges between the objects in the system. And an open system is when there is some net force acting on one or all of the objects. So there is impulse dumped into the system. And so there can be a non-zero delta P total, and that non-zero delta P total is exactly equal to whatever the net force on the system was times delta T. And this F net could be a sum of the forces, or like these F net delta T's could be a sum of the forces that are acting on different objects in the system, right? It doesn't matter. This is just the total. You can think of it as just dumping the impulse into the bucket, and if you have a net non-zero, then you'll get some delta P total that's non-zero. Okay, so let's apply this in a pretty simple example. We have a 3 kilogram object at rest, and then we apply first a force F1 that has these components. So F1 is just pushing to the right for 2 seconds. Then after that, we have another force F2 that we apply with these components. So it's just directly down. We apply that force for 3 seconds, and we want to know what the final velocity of the object is, the magnitude and direction of the final velocity of this object. So let's start by making a momentum chart. We know that P initial is 0, right? The object's initially at rest. And now we need to figure out what our delta P is, which there clearly is an F net here, right? So we know our delta P comes from the net force, specifically the net force applied over time. But I have 2 forces acting sequentially, right? I have one force and then another. So how do I work that into this momentum chart, where I usually think of this as like one thing going in the delta P? Well, I can just put them both there. So my delta P, I'm adding up my F1, which is to the right, and my F2, which is down, to get this net force that goes to the right and down. And these should also be scaled by the delta T's, but here I'm just doing some preliminary vector addition. Yeah?
So you're just kind of adding the values that we have for like the first object and the second object from P initial to get your change in P.
Yeah, and so there's only one object, but the first and second force.
Okay.
Yeah, so here's my object's initially at rest, and we apply 2 forces to it. It doesn't matter that one applies first, that they're not at the same time, but we apply this force and then this force, right? And so we get some net force that's down and to the right. And since 0 plus delta P gives us P final, we get this P final that's just exactly equal to the delta P. Yeah. Yeah, exactly. So this is a momentum problem in 2 dimensions. Okay, so why could I do that? Well, think about what we're actually saying here. This P initial means before any of the forces applied. This is just when the object's at rest. And then P final is after all of the forces have acted, right? This is our final state when everything has occurred, what it looks like. So this delta P doesn't just have to be an instant. Delta P can summarize everything that happened in between P initial and P final. And in this case, there were 2 forces. The resultant final momentum of the object would not be different if these 2 forces acted at the same time, or if they acted in opposite order, or if one acted and then 200 years passed and then the other acted. It doesn't make a difference. At the end of the day, you still apply this force for this long, this force for this long, and those have some effect on our object. Yeah?
So by this reason, we can find P final by adding the coordinates of F1 and F2?
Yeah, and we'll do that explicitly on the next slide. Okay, so here's our momentum chart. It's a pretty simple one. It just says 0 plus some change equals a final momentum. And again, we're noting here that delta P is in the same direction as F net. right? The change in momentum is just equal to F net times delta t. So now let's solve the problem. We're looking for the object's final velocity. The equations we're going to need are just delta p equals F net delta t, and then just our definition of what momentum is to get velocity. Why is this all we need? Well, I mean, if we look at our momentum chart, really what we're doing is evaluating this equation, right? This momentum chart tells us an equation that is p initial plus delta p equals p final. But since this is 0, the equation we're looking for is just delta p equals p final. So we just need to know what that delta p is, which is why I want to solve for delta p. But now we're working in 2 dimensions. So the step we need to make is to break it into x and y components, because those act completely independently. So let's do that. And then we just get 2 equations. Now they are the same ones, but we got the little x and y subscripts. So let's start with the x direction. And sorry, here's the components of our net force, right? We can combine these 2 forces into something that has 3 newtons in the x direction and negative 4 newtons in the y direction. This is kind of maybe not a great way to put it because they act for different amounts of time. So this is a weird way to write the net force, but we won't actually use it because we're going to work components independently. So in the x direction, we have delta px equals F net x delta t. And so we can just plug in our F net x is this 3 newtons, and we know that acts for 2 seconds. And so we get an impulse delivered that is 6 kilogram meters per second. And then we know that our P final is equal to that, right? Because our P initial is 0. So our P final must also equal 6 kilogram meters per second. That's how much momentum the object has after F1 acts on it in the x direction. And if we want to solve for the velocity, we just need to divide that by the object's mass, right? Because we know P equals mv. So divide by the mass, and we get the final velocity of the object in the x direction is 2 meters per second, so to the right. Now we could just repeat the same steps for the y direction. Right now our F net is negative 4 newtons. Our F net y direction is negative 4 newtons. That applies for 3 seconds, and so we get a negative 12 kilogram meters per second impulse delivered, which is also equal to the final velocity or final momentum of the object because we started with 0. And so dividing by the mass, we get the final velocity of the object in the y direction is negative 4 meters per second, so down. And there, we have the components of our final velocity, right? We delivered some impulse to the right, delivered some impulse down. Now the object has this new velocity when it was originally 0. But we're not quite done because the problem asks us for magnitude and direction, not components. So this is a very typical order of a problem you'll see where you're given a problem, you have to break it into components, do your work in terms of the components, and then for your final answer, put it back into this more communicable magnitude and direction form. So let's do that. How do we turn this into a magnitude? Well, we have our Pythagorean theorem. So we just take the square root of the sum of the squares, and we get the magnitude of the final velocity is 4.47 meters per second. So that's our final speed. You could say that's the definition of the magnitude of the velocity. We call that the speed. And then for the angle, we need to do a little work to specify what angle we're talking about. So the way I've drawn it here, you can see our v final is this vector pointing down and to the right, which has a component in the x direction pointing to the right, component in the y direction pointing down. And so if I define theta to be the angle I've labeled here, then I would find this theta with v1y as my opposite and v1x as my adjacent. So I would do inverse tan of v1y over v1x. Right, so you could also write it as tan theta equals v1y over v1x. And I solved to get theta equals 63.4 degrees. And I'm still not done. I need to specify what that angle I solved for means, which in this case is the angle south of east. Or we could also say below the positive x-axis. Or we could say clockwise from the positive x-axis. There's a lot of ways to say it, but as long as we are precise, then it works. One other thing to note is that I used 4 and 2 here, not negative 4 and 2. Right? The y component of the velocity is negative 4. And that's just because when we do our trigonometry, I recommend, and for tangent you actually have to, but I recommend when you do the trig, just use positive values, and you'll always get a positive acute angle, so like something less than 90 that makes sense. And you just need to like use diagrams and words to it makes you know what you're talking about. You can't, and it doesn't get you into this weird territory where your trig functions are going to turn out like, I don't know, things that you don't want or don't know what they mean. So use positive values for your side lengths. So in other words, just magnitudes of the components, and that will make it a lot easier. Yeah. Mm-hmm. Here? Cool. Okay, great. And now that's not the only way we could do it, right? What if I had drawn my triangle like this? Same exact thing, same v final vector, same components. I've just written it differently, defined theta differently, and that's fine. Now instead of tan v1y over v1x, I get v1x over v1y. That's fine, and that works out to be 26.6, which is indeed the complement of 64.4. It's the same thing, except now I have to say east of south, or to the right of the negative y-axis, or counterclockwise from the negative y-axis. And this number is changed from the lecture slides. Someone pointed out there was a typo this morning. If you downloaded the lecture slides, I think this says 36. That's just wrong. Yeah. Yeah, absolutely. So you could also have done the magnitude of the net force, like the magnitude and direction of the net force, or net impulse, I guess, and then, so yeah, we could have done this step, like going back into magnitude and direction earlier on. Yeah, it's just up to you. You get the same answer. Any other questions about this one? Okay, so now we've seen a simple 2D momentum problem. Next, I'm going to do a more complicated 1D collision problem. So still one dimension collision, so multiple objects. And then that leaves for you in DL and FNT to kind of combine them together. So doing more complex, so like multiple objects and 2 dimensions. You have all the tools. It's not that much harder. It's just kind of more accounting. But yeah, so just so you know, that's what this lecture is going to build up to. But first, let's do a clicker question. You have a ball with some initial momentum. So this is its initial momentum vector, not velocity, but momentum. And it has a firecracker in it, and it explodes at some point when it has this initial momentum. And shown here are a bunch of different resulting scenarios where it splits into 3 pieces, and each has their own individual final momentum. Which of these scenarios is not possible? So which of these does not conserve momentum? So I'll open this one up and give you a little bit to think about it. Ooh, we got a rare case where there's at least one answer for each of these. That's always fun. All right, I'll give you 15 more seconds. Let's walk through these together. Okay, so first, what we're looking for is conservation of momentum, which means that we want our total final momentum to equal our total initial momentum, right? Conservation means there's no net change. So our initial is just this upward amount of momentum, right? So we want the sum of all the momenta in each one of these to equal that initial. And so let's go through and check. For A, we have these two bottom momentum vectors that point equal and opposite, right? So those are just going to cancel. And we're left with the net momentum being just the momentum of that piece on the top, which looks to be the same as what we started with. So that works out. That conserves momentum. One key thing to note why this had to be momentum and not velocity is because if this was velocity, if these arrows show the velocity of these objects, if this small top piece in A and the original ball both had the same velocity, they would not have the same momentum, right? Because this third of the ball, this broken piece, has a lot smaller mass, right? So if they had the same velocity, their momenta would not be equal. But since these arrows are representing momentum, then it's fine. And in fact, that means that this small piece has to be moving faster upward than the original ball was, right? So that's just a side point, not relevant to the answer. But A works out. That conserves momentum. Let's take a look at C. Now we have two arrows on the bottom still pointing in the x direction equally and opposite, right? So their x components are going to cancel. That's fine, right? So we're left with no net momentum in the x direction. That's what we want. But then they both have also an element that goes upward. So now we have a small element of upward momentum from each one on the bottom and a little bit more upward momentum from that piece on the top. And so those three can add together and do to give us a bigger upward momentum vector, just like the one we started with. So C is also good. Situation D is a lot like C, except it's even easier. We're just lacking those two equal and opposite outward momenta in the x direction for those bottom pieces. Now it's just summing up three small upward momentum vectors to get one larger one. That also works. E is a little bit trickier. Let's take a look at it. So we still, again, have two momentum vectors on the bottom that have outward components, right? Their x components are equal and opposite. This one points a bit left. This one points a bit right. Great. We have no net momentum in the x direction. But the y direction is a little trickier. Now we have large y components for all three of these, right? So one way we can think about it, well, I'm going to say they all have equal magnitudes of momenta in the y direction. Why? Well, the y component of a vector is just the extent of it in the y direction, right? Like how much vertical ground does it cover? And if we look at these three vectors, they all cover the same amount of vertical ground. Like you could connect the tops of all of them with a horizontal line and connect the bottoms of them with a horizontal line. So despite the ones on the bottom being longer and diagonal, in the y direction they have the same magnitude, right? And each of the ones on the bottom have a positive magnitude in the y direction, or positive y momentum, and the one on the top middle has a negative. So we're left with like one large upward momentum in the y direction, plus one negative momentum in the y direction, plus one positive again. So we're left with one net large momentum vector in the positive y direction. So maybe that explanation got a little messy, but these three y components add to one resulting upward y momentum vector that very well looks like the first one. Yeah?
So although E has one portion in the negative y direction, one of the vectors is pointing up, so those cancel, right?
Yeah, exactly. So that's one way you can think about it. Is like this one and this one cancel in the y direction, and so we're left with one net up if you want. But yeah, so that one does indeed have a net momentum in the y direction. It's good. Now finally, the answer is B. That's why I left it for last. It does not conserve momentum. Let's see why. Same deal. X components cancel. We have equal and opposite pointing out in either direction. But now we have a similar situation where we have three equal magnitude y components, except now two of them are negative and one's positive. So we're left with a net that is negative, which does not match the initial situation. So I like this problem because I don't like when I read it, it makes me think like, oh, this will be easy, and it's like it seems like it should be very easy to pick out, but I think it takes a lot more work to actually decide, and it has a lot of built-in value. Questions about this problem? Yeah. They wouldn't cancel because the two bottom ones would add up to one longer than the top one. Yeah. Yep. Yeah, this is just assuming that there is no net force. Yeah, a lot of times in lecture, I won't be as careful to say like no net force is on a quiz or something like that, but on any assessment, it will be very clear whether there's a net force or not from gravity or something. Yeah. Yeah, we definitely could. We'll more talk about that at like the end of the quarter when we talk about like acceleration. But yeah, it's possible. It gets tricky, so you won't see it with these problems, I don't think. But yeah, the reason we don't often talk about gravity with these momentum problems is because usually we're talking about like objects on a surface, and so there certainly is gravity, but there's also an equal and opposite normal force, so that the net force in that direction is 0. And so everything just happens in one plane. Okay. So like I said, now we're going to pivot over to a collision problem, still in one dimension. And yeah, and we'll work through that. So I spilled chocolate milk over a lot of students' quizzes, and obviously I can't read them, so I have to give them zeros. Those students are not happy with me, and so perhaps justifiably they throw some eggs at me as I'm rollerblading to class. So what we know is that I'm moving in the positive x direction at 5 meters per second, and the 3 eggs hit me, they're traveling in the negative x direction at 20 meters per second. So these students have quite an arm, too. Perhaps it's some student athletes on the baseball team. But yeah, so they throw the eggs at me. I give my total mass is 60 kilograms. Each of the eggs has a mass of 1/4 kilogram, so those are also some really big eggs. And so we want to know how much do the eggs slow me down, right? So I'm moving one way, the eggs are coming from the other direction, we collide, and what's going to happen to my final velocity? So first let's define our system here. It'll be me and the 3 eggs, right? And there's no net force. And this is one of those cases where gravity certainly acts, but because there's a normal force that's keeping me from sinking into the ground, in the y direction they cancel. So there's no net y direction force. And so this is a closed system, no net force, and so our delta p total has to be 0. In other words, the momentum changes will have to be x changes, right? The eggs and I will have equal and opposite changes in momentum, which we'll prove that as we go through. So let's make a momentum chart. I'm going to condense this a little bit, similarly to before where I combined 2 forces that act at different points in times into like one piece of the momentum chart. I'm also going to combine all 3 eggs together because they all have the same behavior. They have the same initial speed. They hit me the same way. They're coming at the same direction. They have the same mass. So I'm just going to multiply everything that happens to the eggs by 3, right? This is really no different than a situation where one egg that had a mass of 0.75 kilograms hit me. That would give us the exact same momentum situation, at least as far as I'm concerned, or like my change in velocity is concerned. But I could also have 3 separate rows, one for each egg, and they just all be identical and add up. Whatever floats your boat. So what we do know is that I have some initial momentum to the right, and so I'm going to make that this big momentum arrow. And then the eggs have some initial momentum to the left. And how did I know to make the eggs arrow a lot shorter, a lot smaller in magnitude than mine? Well, even though the eggs are moving 4 times as fast as me, right? My speed is 20 meters per second, or is 5 meters per second, and their speed is 20 meters per second. my mass is 60 kilograms, and theirs is a quarter of a kilogram. So that difference in mass is much more significant. And so I'll talk about this more on another slide, but they're going to carry a lot less initial momentum than I do. And so we can find our total initial momentum by just adding them. And that will be some net momentum in the positive x direction that's slightly shorter than the initial momentum that I had, because we have to add on this little negative bit from the eggs. All right, and then one last box that I can fill out easily. If we look at this bottom row, we just see P initial plus 0 means that our P final total needs to also be whatever the initial was, right? So this is, again, reinforcing that whatever momentum is in the system to begin with is the same as the total momentum at the end. Now we need to do a little more work to fill in these other boxes, because we have two unknowns in however you cut it. One of the rows, one of the columns, we need to use more information from the problem. And the key piece of information that I want to highlight is that when the eggs hit me, they stick to me, or they break. So I guess this is assuming these are not hard-boiled eggs, which would be even crueler, but the eggs shatter and they stick to me. So this is another case, like if this was a quiz, I would tell you explicitly that they stick, but we'll use our imaginations here, and we know that when eggs hit me, they crack and they will stick. And when objects stick together, that means they have the same final velocity. So that's a very important thing that you need to be able to pick up, and you'll see it in a lot of problems. When objects stick together, so that's the qualitative piece of information, the thing that you should infer and pop into your equations is that they have, after they're stuck together, they have the same velocity. That's that, and that reduces the amount of variables, right? Because then instead of having a V final for me and a V final for the eggs, I know there's just a single V final for all of us, and then, yeah, I have one less variable, and I can actually solve the system of equations. Okay, so, yeah, as I've written explicitly here, my final momentum is just that final speed or final velocity that we share times my mass, and the egg's final momentum is that velocity that we share times their mass. Now this is like something we don't normally do, but I'm going to take the ratio of those two just to see how they compare. I just want to see what the magnitudes, how the magnitudes of them compare. So I'm just going to divide my final momentum by the egg's final momentum, which, because we have the same final velocity, just reduces to my mass divided by the egg's mass, right? So my mass is 60 kilograms. The eggs I'm combining together as just 3 times this 0.25 kilograms. And so I get 80. The magnitude, this is just saying that the magnitude of my final momentum is 80 times the magnitude of the final momentum of the 3 eggs. Why did I do that? Why do I care about that? Well, when I go to fill out this momentum chart, whatever momentum vector I give myself needs to be a lot bigger than the momentum vector that the eggs have. Now, obviously, these are not to scale perfectly, right? Like this vector is not 80 times as long as this, but it's not so important to be that explicit in your momentum charts. Like, as long as you're getting the picture here, you don't need to use a ruler to make sure that everything scales perfectly. But my final momentum needs to be a lot bigger than the egg's final momentum because we have the same velocity and I have a much bigger mass. Now, in writing these, I also had to do a little more work in how big to make these compared to the arrows in the first column, right? And the key to that was, well, I know that the total for both the initial column and the final column needs to be the same, right? I have the same total momentum. In the first column, that meant my initial momentum plus a negative piece, so the total was shorter than my initial momentum. But for the final, I'm adding 2 momentum vectors that are in the same direction. And so my initial momentum needs to be smaller than the total final momentum because I'm adding to it to get the same thing. Right? So that's what told me that this final momentum vector for me needs to be not only bigger than the one for the eggs in the final momentum case, but also shorter than my initial momentum vector. Right? So that's, again, we're still being very qualitative here, but it's important to see the relationship between these two things. And now we're left with just the delta P column. For me, as I just argued, my P initial is larger than my P final. So my delta P has to be negative. Yep. Exactly, yeah. Yeah, that is what's happening. Then the way we figured it out was kind of a little more algebraic. But yeah, that's what's happening. Okay, so yeah, if we figured out that my delta P has to be negative, in other words, I slow down, right? My momentum decreases in that direction. And now there's two ways to find the last bit here. I can either say my initial momentum, my change in momentum plus the egg's change in momentum equals 0. So the egg's change in momentum just has to be equal and opposite to mine. We could also look at the egg row, where we have to go from this initial to the left to a final that's to the right. And so my delta P for the eggs has to be a vector that's like kind of the sum of the lengths, right? Because we have to first erase this momentum, so make up for that. So equal and opposite that, and then add some more in the opposite direction. So maybe that's a harder way to think about it. I think going down this middle row, or middle column, is easier. We know they have to be equal and opposite. But this is how it always works with momentum charts, where you need to first use all of the information that the problem gives you about the starting and ending points, whatever you can. Then there's like this middle ground where you need to like think a little bit harder, and that's the piece where I realized that the V final needs to be the same for me and the eggs. So that's the like still buried in the problem, but takes a little more work. And then your final step, which is like completing it, you have to do some actual algebraic or vector addition, where you need to see what has to be true in order to satisfy these. Yeah. Now let's actually use this momentum chart to solve the problem, because I want to know how much my velocity changed. That's what the answer I was after. So I have my momentum chart, and we know everything there is to know about the initial state, right? I know my mass and initial velocity. I know the egg's mass and their initial velocity. So let's solve for the total momentum, which is going to be the same throughout the whole occurrence of this problem. So we know P initial total is just the sum of our initial momenta. And so if I evaluate that, I have my mass times my velocity, which is in the positive x direction, plus the 3, so multiplying by 3, because there's 3 eggs, their mass times their initial velocity, which is in the negative x direction, so that's negative, and I get a total of 285 kilogram meters per second. So that's my initial total momentum, but it's also my final total momentum, because there's no net change, and so the total momentum is constant throughout this whole problem. So I know P initial total equals P final total, and so P final total is the same 285 kilogram meters per second we just found. Now that I have this vector, the P final total, I can also say that's equal to the sum of the momenta that me and the eggs have in the final state, right? So that's also equal to my mass times my final velocity plus the egg's mass times the egg's final velocity. And now I have an equation where the only unknown is this V final. And here it's emphasized, it's very important that these two VFs are the same. Otherwise, I wouldn't be able to solve it, because I'd only have a single equation with two unknowns. So it was a key to recognize that VF was a single value. And now we can just solve for it, which comes out to be 4.69 meters per second. And I just kind of wrote it this way to emphasize, this is what would happen if you just solve for it algebraically. You get 285 over 60 plus 3 times 0.25 kilograms. But what this really is our total momentum divided by the total mass, right? Because what does that final state actually look like? It looks like me rollerblading in one direction with the 3 eggs splattered all over me, or attached to me. So you can think of us as just one big object with a mass of 60.75 kilograms, right? There's no difference between those two ways of thinking about it. So you didn't have to write m total, that's not actually part of the solution, but I just wanted to illuminate why this answer works the way it does. And there's our answer. So we found that I slowed down from 5 meters per second, and then the impact of these 3 eggs, the impulse they gave me, impulse in the opposite direction, slowed me down. And now me and the eggs are moving forward with this speed. So my speed decreased, and the eggs, their speed decreased a lot, right? They were moving 20 meters per second. Now they're moving less than 5 meters per second, but in the opposite direction. Yeah? Yeah, so maybe our final answer could be 0.31 or something. Yeah, and that's another thing where like the phrasing I'm less concerned about. Like maybe this is the final answer. Maybe you could say I slowed down by 0.31 meters per second, or you could say the change was negative 0.31 meters per second. That's less important as long as it's clear you understand what happened, that I slowed down. Okay, so just to wrap this up, eggs have some small amount of momentum that they transfer to me, and it's oriented opposite mine, so it slows me down. Upon the collision, we exchanged momentum. Like we said, there's no net force, so that's what keyed us off, that the momentum changes had to be exchanges. And afterwards, they're all traveling together with the same velocity. So that's a tip you should carry forward, is that when you hear stick together, or you otherwise observe it, the fact that the V final is the same is very important. Questions about this example? Okay, so again, next step is for you to do a problem like this, but in 2 dimensions. And it shouldn't be too bad. I mean, it's a lot of accounting, it's more work, but each 2-dimensional problem is really just 2 1-dimensional problems, right? Which we kind of illustrated with the first one, where we solve for the x, solve for the y, and then just at the end, you got to do a little trig. Yeah, that's where we're going. So let's ask something new, or kind of new, which is what's happening to the kinetic energy here, right? We have an initial state with objects with mass and speed, and then a final state with objects and mass and a new speed. And so let's calculate the kinetic energy in both cases. Now we can just do our normal kinetic energy. We don't need density, so it's just 1/2 mv squared, like we've seen before. And so in the initial state, our total kinetic energy is just going to be the sum of mine plus the eggs. And so for mine, I get 1/2 times 60 kilograms times 5 meters per second squared. For the eggs, I get 1/2 times 3. Right? I have 3 of these eggs, so I could either put this 3 here or just add up 3 of these terms. But their mass is 0.25 kilograms. Their velocity is negative 20 meters per second. But for kinetic energy, we don't care about the direction. We do need the magnitude, but just that. So the 20 gets squared, and the negative doesn't actually matter. So it wouldn't matter if the eggs and I were moving in opposite directions or the same direction. The kinetic energy doesn't care. It just cares about the speed. So I add them together, and I find that the total kinetic energy of the initial state of this system before we collide is 900 joules. Great. Now let's ask, what does the kinetic energy look like afterwards? Right? Because now we have new speeds, a new situation. So let's solve for the final kinetic energy, which is very similar, except now I plug in V final for each of us instead of V initial. Again, now, so the only difference, I've swapped in this final velocity that we share into the kinetic energy equation, and I find that my total kinetic energy in the final state is much less. It's only about 670 joules. And so what happens to all that energy? Why have we lost kinetic energy? Right? We see that kinetic energy has decreased from my initial to my final state, and we call that an inelastic collision. So in a collision, when your kinetic energy decreases, or your kinetic energy is not conserved, it is inelastic. Where does that energy go? Well, so looking at the left side of this slide, we're going to talk about what happens when it is conserved next, but at the left half of this slide, which talks about inelastic collisions, where Ke total initial is not equal to Ke total final, in other words, we lose some kinetic energy, it's dissipated as things like sound and thermal energy. Think of any collision that we experience in everyday life, or think of eggs hitting me. You would hear a sound, right? And what is a sound? But it's a pressure wave in the air. That takes, as we studied in the beginning of this class, not pressure waves, but pressure is energy density, right? It takes energy to make a sound. And so when something collides, like my hand's clapping right now, the sound that's reaching your ears is some energy, kinetic energy, that was that belonged to my hands as they are moving toward each other, and they stop, and some of it's dissipated as sound. Some of it is also dissipated as heat. When you deform objects, they heat up a little bit. And so, yeah, there's lots of ways that the kinetic energy can be dissipated. But in most collisions, some is dissipated, and so we call them inelastic. Yeah? Exactly, yeah. And the next slide is going to address that a bit. But a point I want to make about both of those is we'll often say, kinetic energy is or isn't conserved, momentum is or isn't conserved. And what we're talking about is within a system. Universally, those things are conserved, right? Energy can't be created or destroyed. Same thing with momentum. But it's when we draw the bounds of our system that we can say within this system, it's not conserved, meaning some left or some entered. And so that's important. Inelastic is whenever they're not the same. You can have a collision that's perfectly inelastic. That's saying the maximum amount of kinetic energy was lost, and that occurs when objects actually stick together. So in the case when the eggs hit me and stick to me, that kinetic energy loss you can prove is the maximum amount that can be lost. You can have some that still bounce off, but some kinetic energy is lost. If I throw a ball at the wall, it's going to bounce back, but you're also going to hear something. So that just tells us that some of the kinetic energy was lost, but not maximally. If you want to go a little bit further, you can actually prove these things to yourself about inelastic collisions and things sticking together. It's not all that you will never need to do it for this class, but it's not hard to show that if two objects are moving and then stick together and have the same final velocity, which is the definition of sticking together, then it's impossible to conserve kinetic energy unless they were just already connected or not moving at all. So that's kind of a fun proof that you can play around with if you want. But yeah, it's not these little details about sticking together means perfectly inelastic, whatever. Those are important or helpful, I think, to figure out what's going on. But you can never go wrong by just checking, like we just did before. What is my kinetic energy initially? Solve for it. What is my kinetic energy finally? Solve for it. If they're not the same, then the collision was inelastic. The opposite of inelastic is just elastic. It means kinetic energy is conserved and happens when colliding objects bounce off each other and lose no energy. So if they lose no energy, they're perfectly elastic. That's not really realistic, right? I mean, think of a collision that doesn't make a sound or doesn't in any way deform something. It's not, maybe at an atomic scale, there could be some sort of collision that's perfectly elastic, but I don't know, in any macroscopic real-world example, we're probably not going to get a true elastic collision, but much like with wires with no resistance, which isn't really accurate, but it's essentially true, we're going to assume many examples are perfectly elastic, like a bouncy ball bouncing off the wall. We hear something, we know it's not perfectly elastic, but it's so close. Just a little bit of kinetic energy is dissipated. That we'll call it elastic. Yeah.
So they say that in space no one could hear you scream, and I was wondering if that's because of the pressure differential between here and space.
Yeah. Well, yeah. That's part of it. I don't know if I'd say because of the pressure differential, but because there's no medium. So there's no gas that's around that can carry this pressure wave. So your vocal cords vibrate and push air, and that's how they dissipate energy. But if there's nothing for them to push, then there's nothing to absorb that momentum, right? What's actually happening is your vocal cord is hitting millions of air molecules, and so there's that momentum transfer. But if there's no air for them to transfer momentum to, yeah, exactly. There'd be a response in your body. So maybe you can think of it, your vocal cords are going like this, and your body is vibrating equal and opposite to that. I mean, it's technically true. But yeah, maybe in space, you could get even closer to a perfectly elastic collision because there won't be sound dissipation. But even then, what objects collide and truly have no deformation, right? There's when things bend and then spring back, there's some energy loss. If you bend a spring, it's going to heat up just a little bit. So I don't know. A lot of collisions we will examine in this class and assume to be elastic. But it'll usually, again, the way you're going to solve these problems is just calculate the initial kinetic energy, calculate the final. Are they equal? Yes, elastic. Are they not? Inelastic. And the one, if you're going to remember any specific situation, I would just think that if they stick together, you know it has to be inelastic. Any other questions? Yeah. Mm-hmm. That's inelastic. What do you, why? Because the energy is dissipated. The energy turns into other things besides kinetic energy. So like if an asteroid hits Earth, there's tons of heat generated, probably a lot of sound. And yeah, so the energy doesn't disappear. It just transforms into other types, just like before pressure turned into potential, turned into kinetic, so on and so forth. Okay, so let's do a quick clicker question to finish off. We have a tiny piece of space garbage. So here, now we have a space example with an initial velocity of 5 meters per second up, so it's moving in the positive y direction. It hits the moon. The moon does not react. What I mean by that is just the moon doesn't move. So we'll assume the moon is outside of the system. And then after the collision, the garbage bounces off and has this new velocity that is to the right and down. And I'm asking two things. Was this elastic? So was kinetic energy conserved? And is the momentum conserved for the piece of garbage? So both of these things. Is kinetic energy conserved? In other words, is it elastic? And is momentum conserved? Which are two separate things. I'll give you 15 to 20 more seconds. Yeah, so that's like momentum. Both of these things are like momentum's always conserved, but for the garbage is it conserved? Okay. Any last answers? I'm going to stop us there. So the answer is B. Momentum is not conserved, but it is elastic, and let's see why. So for the initial kinetic energy, we just get 1/2 m times 5 meters per second squared. For the final, we need to do a little more work because I'm given the velocity in terms of components, right? But for kinetic energy, I care about the speed. In other words, the magnitude of the velocity. So I need to find the magnitude of that with the Pythagorean theorem, just 3 squared plus -4 squared, and I get the same thing. So kinetic energy is conserved in this collision. The piece of garbage is moving in a different direction, but it has the same speed, and so kinetic energy is conserved. This is elastic. But momentum is not conserved, at least for the piece of space garbage. If we assume the moon provides the external force to turn it around, why? Well, the velocity is different, and so the momentum is different. There is a change in momentum, and so momentum, there is an external force. Momentum is not conserved. Maybe an even easier way to see it, initially we have no x component of momentum, and afterwards we do. Right? So there's no way this could have the same momentum. Yeah. Right, yeah. If the moon was part of the system, then we'd have to factor in that the moon is technically going to move a little bit, even if the piece of garbage hits. But yeah, it's easier to think the moon is just this external, immovable body that provides some external force, and that's why our momentum is not conserved. Yeah. I would be clearer about that, yeah. Well, I just say the moon does not react, like as in the moon, if the moon doesn't move, if we tried to make a momentum chart with the garbage and the moon, there would, the moon wouldn't be able to provide any change in momentum because it can't move itself. So the way I phrased it here is maybe less clear, but on a quiz or something like that, I would be more specific.